Good evening, distinguished participants. I have been saddled with the honorable task of introducing our speaker for today's webinar, with the topic, Stimulated Raman Scattering in Gas-Filled Hollow Core Photonic Crystal Fibers. And the presentation is to be made by Professor Philip Rosell. Professor Rosell is an emeritus founding director at the Max Planck Institute for the Science of Light in Germany. He's also the director of the Center for Advanced Light Wave Science in Guangzhou, China. He obtained his Doctor of Philosophy degree in 1979 at the University of Oxford. His interests focus on scientific and technical applications of photonic crystal fibers. He is a fellow of the Royal Society and Optica, and has won a number of awards, including the 2000 OSA Joseph Fraunhofer Award, Robert M. Body Prize, the 2005 Thomas Young Prize of IOP, the 2005 Kober Prize for European Science, the 2013 EPS Prize for Research into the Science of Light, the 2014 Berthold Lebinger Award, the 2015 IEEE Photonics Award. On the note of this citation, distinguished participants and eminent scholars, I invite Professor Philip Rosell to make his presentation. Professor, you have the floor.
Right, so it looks like we're ready to start. Thank you for the nice introduction. It's an honor to be part of this incredibly international conference, online conference. Thank you for asking me to speak. As you already heard, the title of my talk is Stimulated Raman Scattering in Gas-Filled Hollow Core Photonic Crystal Fibers. Since this is a Raman, it has Raman in the name of the conference, I thought I'd talk about this topic. So I work with photonic crystal fibers. You can see some pictures here on the screen, but in particular, I work with hollow core photonic crystal fibers, and these are the ones I'm going to talk about today when you fill them with gas. So let's talk a little bit about these fibers. And the particular kind of hollow core fiber that you see on the screen is one that guides by a mechanism known as anti-resonant reflection. And I'm going to discuss that in a moment. Here's a picture of one of the fibers, anti-resonant reflecting hollow core PCFs. It's a very simple structure. It has a ring of capillaries around the hollow core, and believe it or not, light can be guided in this hollow core with very low loss. And the reason it's called anti-resonant reflecting is that these thin wall capillaries are anti-resonant with the mode in the core, and so they're unable to couple, and so the light remains trapped in the central core. So let me talk a little bit about this type of fiber, a little bit about the history, a short history of guidance by anti-resonant reflection in optical fibers. The very first fiber that demonstrated this was reported back in 2002 by Feta Ben Abid, who was a postdoc in my group at the University of Bath at the time in the UK. It is a fiber with a Kagome lattice of hollow channels in the cladding. And we were surprised to discover that this particular hollow core fiber guided light over an extremely broad bandwidth of wavelengths extending over thousands of nanometers. It was a bit of a mystery at the beginning as to how this actually works, because the cladding in this case did not have any photonic band gap, and we were looking for photonic band gaps. It didn't have any photonic band gaps. You could prove that from theory, so that there was some other guidance mechanism going on. After a lot of thought, we realized that it was the design of the first layer of hollow channels that was critical. They had to be anti-resonant with the core mode. We didn't realize this right at the beginning, but gradually our understanding improved. 10 years later or so, a group in Moscow came up with this very simple structure, which they called the revolver fiber. It looks like the barrel of a gun. And they demonstrated low loss in the infrared with that fiber. Then the group in Bath again in 2012 came up with a similar structure, which is again a single ring structure, I would call it, of capillaries with a rather strange shape. And they demonstrated really impressively low loss in the infrared. Then Feta Ben Abid, by this time he'd gone back to France. He was making fibers like this in France, and he decided to blow up the capillaries around the central core to create this kind of structure, and was able to demonstrate very low loss with that type of fiber. Where we got involved here in Erlangen with this single ring, very, very simple structure with just thin wall capillaries around the core. A group in China, in Beijing, made a fiber with a more complicated sort of, with two capillaries arranged like this around the core, and achieved very low loss in the telecommunications band. And then finally, earlier this year, the group in Southampton has been working on this as well, and they came up with this nested structure with nested capillaries, thin wall capillaries, and they achieved a loss at 1550 nanometers that was less than the loss of the very best solid core telecommunications fibers. A very impressive result, I think. The reason why these hollow fibers are interesting, one of the reasons is that light, of course, travels 1.5 times roughly faster in this hollow core. And there are situations when you like to transmit information more quickly. So there's some advantage in that factor of 1.5. So what about these hollow core fibers and nonlinear optics? What's the advantage of hollow core fiber in nonlinear optics? Well, let's just go back 100 years or so. Lord Rayleigh, who is very well known for the Rayleigh length, which is the length of the depth of focus at the focus of a lens. Take a laser beam, you focus it down to a very tight spot. The spot size and the depth of focus are correlated. If you make the spot size smaller, the depth of focus becomes shorter. So this means that the benefit of the higher intensity at the focus is cancelled out by the shorter depth of focus if you want to keep light tightly focused over a long distance. The hollow core fiber allows you to overcome this apparent this limitation of the physics. It's impossible to keep light tightly focused in free space. It just doesn't work. Light diffracts. A laser beam will diffract. But if you focus it and launch it into a hollow core fiber, you can keep the light tightly focused over an almost infinite depth of focus. And in the very best versions of these hollow core fibers, the product of intensity and length, intensity in the core and the length, is something like 10 million times greater than a focused laser beam, which is a massive factor of increase. It's not surprising that this has caused a revolution in nonlinear optics in gases. And in fact, back in 2002, when Feta Ben Abid reported the Kagome hollow core fiber, we also reported stimulated Raman scattering, a hydrogen-filled fiber. The same fiber filled with hydrogen gave an extremely low threshold for stimulated Raman scattering because of this huge path length. And it was published in Science. And Mike Downer back then said that he thought a new era in the nonlinear optics of gases is about to begin. And I think he was quite correct. So I hope I'm going to tell you a little bit about some of the results over the last 30 years or so. So let me talk now about another characteristic of hollow waveguides, which is chromatic dispersion. If you're working with ultra-fast, ultra-short pulses and looking at nonlinear optics, group velocity or chromatic dispersion is absolutely key. It's well known that any hollow waveguide will support modes which have anomalous dispersion, which is to say that bluer light has a higher, it travels faster in group velocity terms. This is a purely geometrical effect, which has to do with the ratio between the diameter of the hollow core and the wavelength. And if the wavelength is a large fraction of the diameter of the core, the anomalous dispersion is higher. If we think about a material, bulk material perhaps, that has normal dispersion, well understood, you can find lots of materials like that have the opposite sign. The bluer light travels slower. And if we combine these two things, we have normal dispersion of the material and anomalous dispersion of the hollow core. So what you actually end up with in terms of dispersion is the balance between these two effects. And of course, if this material is a gas, you're free to change the pressure of the gas. And by changing the pressure of the gas, you change the influence of the material in the core, and you can actually tune the dispersion, which is a very exciting development in optical fibers. Prior to this, there was no way to change the dispersion of a fiber once you've made it. So let's just think about this pressure tunable dispersion in one of these anti-resonant reflecting photonic crystal fibers. I already talked about some of the advantages. One I didn't mention was that the overlap between the light and the glass in these hollow fibers, these anti-resonant reflecting hollow fibers, is extremely small. This gives you a very high damage threshold, so you can work at extremely high intensities and not damage the fiber. But the key thing is the pressure tunable dispersion, which is ideal for controlling solitons and related nonlinear effects. You simply turn a knob in the laboratory and you can change the dispersion. It's like an experimenter's dream to be able to do this. So let me show you just some simple modeling of this. An evacuated hollow fiber with no gas in it would have an anomalous dispersion over this huge frequency range or wavelength range. You can see the scale. And as we add more and more argon gas, 2 atmospheres up to 30 atmospheres, we can lift the whole dispersion landscape upwards and create a pressure tunable zero dispersion wavelength as a result. So dispersion is normal up here and anomalous down below. So we have a tunable system. So this turns out to be extremely important for nonlinear optics, for example, for extreme pulse compression and generation of ultraviolet light. So I'd like to talk about this next. This is about soliton self-compression and dispersive wave generation in the deep and vacuum ultraviolet. So I'm going to show you first at the top here. This is a picture, a photograph of one of our experiments. These are gas cells at each end. This is the fiber in the middle. And inside the fiber, there is argon gas in this case. I'm not going to talk about hydrogen yet. I want to just talk about argon gas, which doesn't have any Raman gain. Working with pulses of 30 femtoseconds, about a microjoule of energy. If you look at the numbers, this means that you're launching a soliton with soliton order of about 7. So it's a higher order soliton that's guided in the hollow core, which, I remind you, has anomalous dispersion. And in the experiment, we don't see anything from the side, and all of a sudden, at some point, the fiber begins to light up very brightly. And this happens because the soliton self-compression causes the duration of the pulse to shrink. And in fact, it reaches close to a single cycle duration here at the temporal focus. And at this point, all kinds of higher order nonlinear effects, including higher order dispersion, come into play, and the soliton breaks up. If we look at the spectrum explodes at the temporal focus. It has to, because we've got a very short pulse. But the spectrum extends into the normal dispersion regime. So, and then it's able to shed energy. The soliton sheds energy into an ultraviolet band, a dispersive wave band, it's called, in the ultraviolet. Now, one of the really nice things about this ultraviolet band is that it's first of all quite efficient. 10% of the energy is converted to the ultraviolet. Secondly, it's pressure tunable and energy tunable. So we can tune the wavelength of this band, which is extremely nice if you're working in some kind of experiment where you want to tune the frequency. Just to show you some experimental results from 2013. Here, these are a whole series of experiments with different fibers and different gases, producing narrow bands of radiation all the way from the visible down to the vacuum ultraviolet, with different noble gases in this case. You notice that we go from xenon to neon. The reason for this is that as the photon energy increases, you're more and more likely to ionize the gas. So you need to choose a gas that has a high ionization potential if you want to generate photons in the vacuum ultraviolet. So hence the reason here for using neon at this point. You can extend further into the vacuum ultraviolet by choosing helium. So these are some experiments. This has to be done, of course, in vacuum, the experiments. We were able to extend this radiation right down to close to 110 nanometers deep in the vacuum ultraviolet by using helium, which has an even higher ionization potential. Okay, so what's this useful for? Well, there are many things you could think it was useful for. There are very few sources of very short pulses in the vacuum ultraviolet. So given that there are no sources, there's been very little research using sources like this. But one of the very first experiments was on angle resolved photoemission spectroscopy in this paper by Bromberger and et al. In 2015, it appeared. They needed a source of 145 nanometer radiation in order to produce photoemission from a surface. So that was one of the very first applications of these sources. So what are the other reasons why pulse compression and ultraviolet light generation are important? Well, one of the things about hollow core PCF and these experiments is that extreme pulse compression can be achieved at pulse energies that are about 1,000 times lower than in the traditional experiments that use wide bore capillaries. These traditional experiments need energies of maybe up to 10 millijoules, which is about 1,000 times greater than the energies we use. We use microjoules. This has an important consequence experimentally. It makes it possible to increase the pulse repetition rate from kilohertz up to tens of megahertz, which is very important. It's often you'd really like to have a much higher repetition rate for all kinds of experiments. It also means that frequency combs and optical clocks are possible now in the ultraviolet. They're feasible for the first time using sources like this. And it also means that in a commercial sense, that large-scale laser systems can be replaced with compact tabletop lasers potentially, which will bring ultrafast laser systems to every laboratory potentially. And this opens up all kinds of opportunities for studying femtosecond dynamics in biology, for example, using deep and vacuum ultraviolet pulses. It may also be useful for advances in fundamental physics. Here's one example from the optical clock field, people who build optical clocks and frequency combs. It turns out there's a nuclear transition which is optically accessible, very unusual thing to find. Normally, the transitions we use are electronic, but this is a nuclear transition in thorium-229. It has not yet been optically detected. It's been predicted, but to detect it, you need to have a source of radiation at 159 nanometers. So we think these ultraviolet fiber-based sources will be ideal for building the very first optical nuclear clock. If you're interested, that's a very nice review here by Beeks et al. At the top of the reference. Okay, so that's introducing nonlinear optics and ultrafast nonlinear optics in gas-filled photonic crystal fiber using noble gases. Now I'd like to move on to Raman scattering. And I'd first like to talk about impulsive Raman scattering in hydrogen gas. Hydrogen has two Raman transitions, one at 18 terahertz, which is a rotational transition, and the other at 125 terahertz, which is a vibrational transition. And if you use a very short pulse, just like ringing a bell, you hit a bell with a hammer, it rings. If we hit a hydrogen molecule with a very short optical pulse, we can make it ring like a bell. And once it's ringing, we can then use it as a phase modulator. So that's the simple physics of what I'm going to show you. So let me show you, first of all, a comparison, an experiment where we compared the generation of of dispersive waves, of ultraviolet dispersive wave. We compared it in a fiber with argon and with hydrogen. First of all, with argon gas, this was the dispersive wave generated at around 195 nanometers with argon. Different pulse energies, but basically you can see it's around about 195 nanometers. Now, if we replace the argon with hydrogen and arrange things so that the two systems have the same effective nonlinearity and the same dispersion wavelength, this is what you see with hydrogen. You see the spectrum is vastly extended down into the vacuum ultraviolet, and you get a peak at 8.6 eV, for example. Another peak here. So it's a dramatic difference that the presence of the Raman response has on the spectral extension in the vacuum ultraviolet. So question is, why does this happen? What's the explanation for this? Well, it's actually quite simple, at least in principle, but to model this is not so easy. If you want to do some modeling of what's going on here, numerical modeling, you need a unidirectional full field equation, not a slowly varying envelope equation, but you have to work with the actual fields, and you need to include all the different effects, such as the Kerr effect, Raman effect, and ionization effects. So these are snapshots of how the pulse looks at different positions along the fiber, 4.5 centimeters, 6.5 and 7.6 centimeters. As the pulse compresses, you see we start with a pulse that has maybe 30 femtoseconds duration. Maybe it's a little bit shorter, but it's getting short enough to excite the rotational motion of the molecules, or rotational vibration of the molecules, which is 18 terahertz. We begin to see this blue curve is the rotational response, the rotational coherence. As the pulse gets shorter, we get a very sharp feature. As it self-compresses, it starts to get short enough to excite the vibrational transition, which is 125 terahertz. This is this orange curve oscillating much more quickly. And as the pulse gets even shorter, this vibrational response gets stronger and stronger. And you notice that the pulse duration, after the pulse is gone, this Raman response keeps oscillating. So you can use that as a phase modulator. And in fact, that's the reason why the spectrum extends so far into the vacuum ultraviolet. The Raman vibrations act as a phase modulator and will transfer photon energy further out into the vacuum ultraviolet. Very dramatic effect. So I'm going to continue now discussing Raman scattering, but in a very different way. This is what I like to think of as imposing molecular order on the molecules. I mean, normally they're just banging around, just randomly doing what they do. But using laser light, you can impose molecular order on the molecular motion, and use the molecules in a kind of nonlinear Raman holography. I like to think of it, nonlinear holography. And we use this for quantum state upconversion of single photons. Let me just talk about the idea first of all, where if you operate close to the zero dispersion point and you plot out the dispersion as a function of wave vector here and frequency, so this red dot is the zero dispersion point. If you go to frequencies above the zero dispersion point, the curvature changes, and of course the group velocity dispersion depends on the curvature of the curves. And up here, the higher frequencies travel more slowly, so we have normal dispersion. And down here, the higher frequencies travel more quickly, so we have anomalous dispersion. Now, let's suppose we pump the system. Let's suppose it's a fiber, and we launch in some light at a higher frequency up here, at the red dot at the top, and we turn up the power. Then stimulated Raman scattering will start at some point in hydrogen. We get a certain Raman frequency shift, omega r, and we will generate light at a different frequency. The Stokes light will be generated at this lower red dot. And this happens because we create a coherence wave in the molecules, in the population of molecules with a certain frequency and a certain wave vector. I can just to illustrate what's going on here, the pump light and the Raman and the Stokes light interfere with each other. They produce interference fringes that travel. Of course, they travel at a group velocity given by the expression up here. And this interference pattern drives the molecules which are oscillating. So you put energy into the molecular motion, but that energy is not random energy. It's energy that has low entropy. So you can extract that energy at a later date. And you can do this by launching light in at a much lower frequency here on the left. Use the same coherence wave. And if the conditions are right, you'll be able to convert light in a linear process from a lower frequency to a higher frequency. So it's a kind of Doppler shift plus Bragg scattering, both there together, this Raman upconversion process. So we create the nonlinear hologram up at the top, and on the other side of the zero dispersion point, we use a nonlinear hologram. We read it out, okay? This works extremely well in experiments. So I'm showing you here the spectrum extending from the visible to the infrared. And we pumped the system with 532 nanometer writing signal. You can see the first Stokes and the second Stokes bands. So that prepares the hologram. We then put in a broadband signal. So this blue signal is the signal we wanted to upshift. You can see it's fairly broadband. And through this nonlinear holographic process, this signal is upshifted to a much higher frequency. You can see its shape is preserved very accurately. It almost has exactly the same shape. And really what's amazing about this is that the conversion efficiency is 70%. So we convert 70% of the energy in this signal to a higher frequency. So it works extremely well. So with this result, which goes back to 2015, we published this. We recently thought, well, it would be interesting to see if we can because this is a linear process, we should be able to upshift the frequency of a single photon to a different wavelength band, upshift the frequency, and preserve its coherence. So this is what we set out to do. We used hydrogen-filled single ring holocore PCF. These are some pictures of the fiber we used. Just happened to have eight capillaries around the hollow core in this case. It guided very well at all the wavelengths we wanted in the experiment. And then doing calculations on the pressure tunable dispersion. This is basically, these are these S-shaped curves that are drawn in a slightly different way. This is wave vector, this is frequency. Say if we took a pressure of 80 atmospheres in this case, we could pump at a certain frequency. We generate a coherence wave, which is this white arrow, and we want to reuse the coherence wave at 1425 nanometers to upshift the photon frequency. If you do that, there's a certain amount of dephasing, so it's not going to work very well. If we tune to a much higher pressure, to a much lower pressure, 60 atmospheres, once again, we have detuning here. But if we tune to 70 bar, we get perfect phase matching in this system. So this white arrow can be moved over to the dotted arrow, and they're both exactly the same length and exactly the same slope. So we have perfect phase matching. So this was very, very promising. So in the actual experimental setup, we used a photonic, well, it's not exactly a photonic crystal fiber. It's a fiber with a solid core. It's one of these Y-shaped structures. It looks a bit like a Mercedes symbol. This was designed so that we could generate biphotons because we needed to have pairs of photons that were correlated at 1425 nanometers and 849 nanometers, pumping at 1064 nanometers. So with these two signals were then separated at a dichroic beam splitter into the 849 and the 1425. The 849 was sent around here, but the 1425 was taken and launched into the hydrogen-filled holocore fiber along with the pump laser at 1064. And here the fiber was used to upconvert the 1425 photons to 894 nanometers, the upshifted idler in this case, as we call it in the idler in the signal. And then having got these two signals, we use superconducting single photon detectors to look for correlations, to measure correlations between the two photons and compare the correlations between these two signals and the two original signals and see if there's any degradation in the correlation between the photon pairs. So we did the experiments. We confirmed that 70 bar was the ideal pressure. The quantum efficiency was 70% at max. It peaked at 70 bar, which is what we expected. And these are experiments of the idler count rate as a function of time. As we say, we have the pump off, first of all. We turn the pump on. We get strong conversion, 70% converted to 894 nanometers. And these are the dark counts when there's no light around at all. So the system worked very well. We then did the measurement. We then measured the second order correlation function using this as a standard approach. This was the original correlation function that we got for the biphoton pairs. This was the correlation function for the upshifted pairs. It's almost identical. And really, these are almost indistinguishable from each other. So we have almost perfect preservation of the correlation of the photons after upshifting one of the biphoton pairs. So that was a successful experiment, and we're very happy with that, and I think it may lead in some interesting directions given the interest in quantum optics these days. Before leaving this structure, this discussion, I'd like to talk a little bit more about this S-shaped curve and talk about gain suppression, coherent gain suppression, which was something that was actually predicted by Nikolai Bloomberg in a way back in 1964, but it turned out to be very difficult to observe in experiment. There was no good way to observe this very, very easily in experimental. The hollow core fiber is an ideal system for observing this gain suppression, but let me explain what gain suppression is. And we take our S-shaped curve and we adjust the pressure so that the pump radiation is coming in exactly at the zero dispersion point. And we choose the system so that the coherence wave that is needed for down conversion to the Stokes is identical to the coherence wave that is needed for up conversion to the anti-Stokes. And of course, if you turn up the power, you normally expect there to be a Stokes signal, and maybe you'll see some anti-Stokes as well. However, that's not what happens when you have this exact condition. And we can start to think about this. And I'm going to tell you a little story here about what actually happens. We send in a pump photon, this green thing, and there's a vacuum photon coming in at the Stokes frequency. There's a molecule sitting here. Then if you have a scattering event, the molecule would take energy from the pump photon and will start to rotate in this particular case. And then we get a downshifted photon coming out, which is a Stokes photon. Now you could imagine another pump photon coming along sometime later, seeing the excited molecule, scattering off it, and generating an upshifted photon, an anti-Stokes photon. Now, if you go from the beginning of this to the end, the molecule is in exactly the same state. We haven't put any energy into the molecule, but we have created a pair of photons at the Stokes and the anti-Stokes frequencies. So we have a different output from what went in. But it seems as though you wouldn't get any gain because the molecule ends up in the same state as it started. This explanation actually is not correct. In fact, Bloomberg had pointed out that this explanation is wrong because you see absolutely no anti-Stokes photons at the suppression point. And these are this is a measurement done in the experiment of the strength of the Stokes signal as a function of pressure. In this particular system, we get gain suppression, this exact condition, at about 24 bar or so, 24 atmospheres. This is the Stokes signal when we're operating away from this condition. We get a nice fundamental mode in the Stokes signal. And as we change the pressure, as we approach the gain suppression point, the fundamental mode disappears and we get a higher order mode. In fact, the Raman gain is still there for the higher order mode because it is not gain suppressed. It has a different dispersion. And then we tune the pressure higher, we come back to the fundamental mode. But the most remarkable thing about this is that the anti-Stokes signal, which is quite strong and has sidebands, but when we actually hit the gain suppression point, the anti-Stokes signal dives down, I don't know what it gets to, minus a few hundred dB. It's basically nothing. There's nothing there at all. So it's showing that this gain suppression really works. So this is, in fact, one of the very first measurements where these anti-Stokes peaks, here, these peaks on either side, were actually observed experimentally. They had been predicted, but not actually seen in experiment. Okay, so let me see. My next topic, so I've now talked about this S-shaped curve. I've talked about Raman nonlinear holograms and the kinds of things you can do with these fibers. The final topic I want to introduce has to do with circular birefringence and the things you can do with this in connection with rotational Raman scattering in hydrogen. So the kind of fiber we're operating with is here's one of these single ring fibers as I've described them, but it has been twisted during manufacture. So it has a chiral structure. It's a bit like this building in Sweden, in Malmö, famous building, which has a chiral building. But if you do this to one of these hollow core fibers, you create some circular birefringence. These are just some measurements of a particular fiber. You get a birefringence, in this case, of order 10 to the minus 7. It can get up to 10 to the minus 5, depending on the structure. It may seem very small, but a consequence of this circular birefringence is that you can very stably, very robustly preserve circular polarization state. which is ideal for experiments involving circular polarization state. If you know the circular polarization is maintained, you can do all kinds of very nice experiments. I'm going to talk about stimulated Raman scattering between vortex modes in one of these fibers. First of all, how do we make the fibers? Well, one way to do it is by post-processing. This is how we did it at the beginning. You scan a carbon dioxide laser beam along the fiber while spinning one end. And these carbon dioxide radiation softens the glass. So anybody could do this. You get some fiber, you build a setup like this, you can create a chiral photonic crystal fiber. These days, the most common technique we use is to spin the preform and draw the fiber from the spinning preform. This works extremely well. You can make very long lengths of chiral fiber in this way. So let's now think about a chiral holocore fiber and think about rotational Raman scattering. Now I'm going to just introduce the gain, the stimulated Raman scattering, the Raman gain that you get in rotational Raman scattering in hydrogen. And the analysis of this, it's not so incredibly straightforward. You need to be very careful with the analysis, but you can read these papers. But the result is shown in this plot. This is the Stokes gain that you get for different conditions between the pump polarization state and the Stokes polarization state. So if we have a pump polarization state which is right circular, and we seed the system with a Stokes signal that's also right circular, we get a gain of 1 on this scale. If we seed the system with a Stokes that is in the left circular polarization state, we get a gain that's 6 times higher. That's a huge factor of increase in the exponential gain. So naturally, this conversion process will dominate. If we launched in left circular, similarly, the right circular will see very high gain, and we get the other conditions for linearly polarized light. But I want to focus in on the case where we're using circularly polarized light. And let's have a look at the frequency versus wave vector diagram for one of these fibers. So this is the right circularly polarized dispersion curve, and the left circularly polarized dispersion curve is slightly odd scale here. This is why they slope backwards, but never mind. These are the frequencies, the pump frequency, the pump wavelength, the Stokes wavelength, the anti-Stokes wavelength. Now, if you look at this, if we pump at 1030 nanometers, we pump in the right circular polarization state, we create a coherence wave that gets us down to this point on the left circularly polarized branch, and this will have high gain because it's 6 times higher than the other. We'll also get some gain on the same curve here, the right circularly polarized curve, but the gain is 6 times lower. Okay, so you do an experiment on this. You do it with the twisted fiber, which maintains circular polarization state. And in this case, we launched in right circularly polarized pump light and observed that we got right circularly polarized Stokes light coming out of the fiber in the twisted case. So although the gain was 6 times lower in this case, we nevertheless still saw we saw the same polarization state of the light in the Stokes. Very unexpected, but a direct consequence of the circular birefringence in the chiral fiber. If we take a fiber that was untwisted, on the other hand, then the high gain branch, the high gain mechanism here, which it dominates, and we get a very strong Stokes signal in the opposite polarization state, in the orthogonal polarization state. And you see this very clearly in the experiment. Okay, that's to do with the circular polarization state and the conversion processes and so on. Now I'd like to move on to vortices. And in order to do that, what I'd like to do is talk a little bit, just for a minute or so, about orbital angular momentum, spin, and topological charge for circularly polarized modes. All right, this, of course, I'm referring to work done by many other people, including Pancharatnam way back in 1956, and Mike Berry generalized these ideas in 1984. So this LA parameter is what I call the orbital angular momentum order. It's the number of cycles of 2 pi as we go around the azimuth. So we're going with this, just suppose this is a beam, and I'm looking at the polarization state around the circle in these animations. What I'm going to do is stop this. Let's stop it there. So in this case, this orbital angular momentum order, it emerges when you do the theory in cylindrical coordinates. And in order to solve Maxwell's equations for cylindrical structures, you have to use cylindrical coordinates. But if you do that, you find that you get this OAM parameter coming out, this LA, which tells us how many cycles of phase the field experiences as we go around the azimuth. And if LA is 0, then in cylindrical coordinates, the field will point in exactly the same direction relative to the direction of the radius at all points around here. So this azimuthal order here, the OAM is 0. Spin might be, say, +1. The topological charge is the number of zeros or singularities in the field actually on axis. So if we look at this picture, you can see the field's pointing upwards here, and it's pointing downwards here. And so you'd expect these fields to exactly cancel on axis, which is exactly what happens. So we don't have any on-axis field sorry, we have one on-axis field singularity in this case because the fields have to cancel in the center. If we, on the other hand, we take the case of LA as -1, so you can see that relative to the radius, these arrows are rotating. So this one has changed its direction relative to the radius in each case. But if you do this correctly, we end up with a linearly polarized mode. And in this case, there is no field discontinuity on axis. So LT, the topological charge, is 0 in this case. And this is the fundamental mode. And if we go to LT is +1 in this case, you get a more complicated pattern. But once again, there are field zeros on axis in this case, actually 2 field zeros because the topological charge is +2. So that's an introduction a little bit to this field. It's very confusing in the literature to kind of understand it sometimes because the terminologies used are different. But let me talk now about some experiments in my last few minutes. First of all, these twisted hollow core photonic crystal fibers, they guide vortex modes and maintain the vorticity very well. These are some experiments done. We have a laser beam coming in. We split it into 2 paths. One of the paths we use as a reference beam, and the other path is sent to a spatial light modulator to generate different patterns, different phase patterns. And we can, for example, generate a donut mode, which is sent into the twisted single ring photonic crystal fiber. We then do an interference experiment between the 2 beams. And if you do that correctly, you can produce these nice spiral-shaped interference patterns that are directly related to the sign and magnitude of the topological charge. This would be LT is +1, ring-shaped mode, and the interference pattern looks like this. And theory confirms these results very nicely. Now, with this system, we can launch different orders of topological charge and so on. But let's just have a look at some other topological charges. LT is 2, for example. LT is 3, so we have 2 on-axis singularities and 3 on-axis singularities. And what was beautiful, really beautiful about this fiber in the experiments was that it wasn't absolutely perfect. So it turns out that the field singularities kind of separated out. They weren't in exactly the same point. So they separated out, and you could see in the experiment these 2 dark dots. They were separated sort of more or less in the center of the core. And this was confirmed by finite element modeling using the exact structure that you'd expect to see this. We also saw a case where there were 3 zeros, not so easy to see perhaps, but there were 3 distinct zeros here, once again confirmed by numerical modeling. So we were able, therefore, with this fiber to guide these complicated modes over long lengths of fiber and preserve all their characteristics. There's circular polarization state and so on. So let's now think about some experiments on stimulated Raman scattering between these modes. So this is the system we used. We're using a Caro single ring fiber, as I mentioned. We have pump light, beam splitter. One branch is sent because we want to actually do seeded rotational Raman scattering in this case. So we'd like to generate a seed signal, a seed Stokes signal, which is 18 terahertz shifted from the pump frequency, because that's the rotational frequency shift in hydrogen. And the nicest way to do this is to use actually a photonic bandgap PCF, not a PCF like this, but one that has a photonic bandgap, because you can design that to have a narrow guidance band. And if you do it correctly, the Stokes will lie within the guidance band, and so you get a very clean Stokes seed signal generated. So this Stokes seed signal is sent around and combined with the pump, and the pump light, you can adjust the vortex, the vorticity of this with a spatial light modulator, and then they're both launched into the twisted photonic crystal fiber. And all kinds of diagnostics coming out. Here's an example of one of the plots of one of these donut modes that were seen in this experiment. Okay, let's now look at some of the results from this. So SRS between vortex modes. Well, it's if you have vortex modes with different values of this orbital angular momentum, this will or topological charge. This requires an orbital coherence wave. You need some orbital angular momentum in the coherence wave for this to work. So again, just reminding you, we're using a Stokes seed mode in this case. So let's see. Now we're going to pump. In this case, we're pumping. Let me explain the diagram perhaps first. So this is the topological charge along the bottom, different values to the topological charge, which has to be an integer for circularly polarized light. We have the Stokes band at 1097 nanometers, the pump band, and the anti-Stokes band. And the full line is left circular, and dotted line is right circular. Okay, so that's what this diagram is about. Now let's suppose we pump at right circularly polarized light, and we pump at 1030, and we launch in topological charge -1, which is this point. We turn up the power. You'd expect to see a Stokes signal with topological charge of 0, so a fundamental mode, and that's exactly what you see over here on the right. You see a beautiful fundamental mode which has LT is 0, and in order for this to work, the coherence wave has to produce an angular momentum order of -1 in order for the scattering to work. At the same time, you can, once the coherence wave is generated, you can then upconvert from left circularly polarized light to right circularly polarized light to an anti-Stokes band. But that conversion process will be different from this because it will generate topological charge -2. So you get a much more complicated pattern. It's not as clean. This is topological charge -2. We were convinced it did, and it's rather messy looking. Well, it's a tough experiment to do very accurately, but we're pretty sure we got topological charge of -2 in that case. Now we can also do another experiment, this time with co-polarized pump and seed. So we have pump, which is right circular. We have Stokes seed, which is right circular as well. So this time the gain will be lower, 6 times lower, as I mentioned already. But once again, we got mode patterns that look very similar to the ones that I've shown you already here on the right, but with lower gain. And finally, you can also do an experiment where both the pump and the Stokes had the same topological charge, which is -1 in this case, in which case we're converting directly upwards in this diagram from right circular to right circular, right circular to right circular Stokes. And in this case, the Stokes signal looks exactly like the pump signal. It's a ring, it's a donut mode, and also the anti-Stokes mode is also a ring mode. So everything kind of sort of fits together very nicely. And the overall conclusion of this work is that rotational Raman scattering in chiral photonic crystal fiber requires, for that to be efficient, it requires conservation of 3 things. Obviously, the photon energy has to be conserved in the process, but you have to preserve linear momentum, angular momentum, and spin. You have to think about all 3 of those things and combine them in the correct way in order for one of these processes to actually work. Okay, that brings me to the end of all the science that I wanted to talk about. Just finally, I'd like to acknowledge the huge number of people who worked with me over the last 30 years, more or less it is. I think these are some of the photographs of them over the years. From the University of Bath to University of Erlangen to this Max Planck Institute. So they've been fantastic colleagues and wonderful researchers. So a lot of the results we got I really owe a huge debt to these people. And with that, I've reached the end. And thank you for listening. I hope everything's worked all right. So over to the chair.